Okay, thanks for coming. I don't have to introduce myself, as everyone knows me. We have a few. Yeah. Okay. So this is a sort of replacement seminar. That's why I couldn't make up my mind what to present to fill in the gap. And at the end, I decided to do this. We had a master's student, Alexandre, who is back in Mozambique, and he had done work. That also was an emergency work because he had been planning to do something else. He had ethics approval, but the data didn't come through. And then he came to me and I said, okay, you are from Southern Africa. Let's look for data from Southern Africa. And then that's how we ended up in Tanzania. He's not from Tanzania, but I like Tanzania because that's one of the most peaceful African countries. It's also notable because it's a country that had a president live peacefully. Julius Nyerere, old socialist leader from the 1970s, 80s, one of the African brothers. They used to come to Ethiopia. Mugabe, a few others brothers. He left, and that's how peaceful he was. I don't think it's as good in terms of government as it is, but still, Tanzania is a very peaceful country. So that's also a caveat. That means this was an opportunistic research. None of us are experts on Tanzania. So when I had to do this, I thought, well, I might as well talk about this generalized true random effects model, and I will describe why it can be interesting and what we have been doing. There is a message on the chat, upside down view from Zoom. You guys are upside down. So what I will do is I will spend most of the time talking about the GTRE model, and a little bit at the end talking about the application. Those of you online, just shout if there is anything else upside down. Okay, so what are these models? I think in a way this is not just about efficiency, but in general about panel data models. How do you separate individual effects from other things? The moment you go from cross-sectional data to panel, you get a richer data set, but you get more problems, and you don't have an excuse to just get the easy way out. I'll talk about SFA. I don't want to bore you about SFA because if you are in production economics, you know what SFA is. But if you are not, maybe it's just one of those models that you know about, but don't exactly know what the details are and what's simple, what's sophisticated. Then talk a bit about panel data, how they allow for heterogeneity, persistent efficiency. These are both individual effects. Then how do you estimate it? The big problem in SFA is even 40 years later, we do not have a robust software for estimating models. Anyone working here has had a problem, something not working. And this is a major challenge because we don't have enough people writing software. That means people have to struggle. In fact, there is a huge amount of time that's wasted with people trying to figure out how to estimate something. Months and months. So we will talk a little bit about that. And the more complex the model, the more the problem and then application. Well, now it's standard to talk about inefficiency, but traditionally economists did not talk about efficiency. They just assumed efficiency only. So if you look at all the work from the early period, notable people are like L. Hedy at Iowa State and many others, and the microeconomists, they don't talk about inefficiency. Why would you talk about inefficiency? Producers are economically rational. Why would they be inefficient? They have to be efficient. Okay, and production economics is mainly about optimization, how to estimate production functions, whether it's Douglas or later Translog and so on. And even at some point in development economics, there was this famous hypothesis called efficient vertical hypothesis. So this is against the backdrop of how economists thought in the 40s, 50s, when development economics was taking off. Many economists obviously thought that developing country farmers were backward. They were, more engaged in social celebrations and festivals and so on. They could not be efficient. They could not be rational. And in the 60s, this person, Schultz, Did he take the Nobel Prize? Yeah, he did.
Only young economist to win the Nobel.
Yeah, he shared it with Luz or with separate? Yeah, okay. So he's the only economist taking the Nobel Prize. He came up with this idea based on research in India, showing that farmers are actually efficient. They might be poor, which means their yields, because of the resources they have, might be limited, but they are efficient. So this was the accepted wisdom for a while. Obviously, the economists were looking for more and more ways of creating new ways to research. In the 50s, there was well-known research done by someone called Farr. I was pulling out his paper for the production economics unit, and I was surprised to see how extensive his work was, because sometimes when we see old seminar work cited, we just assume it's short paper, simple paper, early idea, but it's not very elaborate. He had this idea of doing efficiency using DA type models, but they were not called DA models back then, because in the 50s, no one had the name DA. They called them activity analysis. The mathematician Koopmans and Derbo, the famous microeconomists, these guys were working actually on these models, but they didn't call them DA. The management science people came in the 70s and called them DA, and the literature exploded. Now you get thousands of DA papers every year. But on the econometric side also, there were people working on these things. So since the 70s, it has become a norm to incorporate inefficiency in models. So if you were studying here, your master's or PhD, you got farm data, and you said you are going to do what L. Hedy did in the 1960s, people would say, what are you doing? You have to check. Huh? Check. You have to incorporate efficiency. Yes? Yes. So efficiency analysis is a vibrant area. Of course, when you think of the applications, what do we use it for? Well, you might say, are we measuring efficiency and trying to show whether we should be doing extension better and so on? I think it's more than that. In fact, in the European countries, they use this efficiency analysis to inform regulation. So if you are regulating utilities and you are adjusting utility prices based on cost, you cannot let the utilities just decide what the cost is going to be. You have to benchmark them against others, and that's what we are doing in the Netherlands and so on. So it's not just about all the economics; it's also about regulation and many other things. And you can apply to anything. You don't have to be goods production. It could be hospitals, it could be schools, it could be anything. So this is and so on. So the basic stochastic frontier model just adds one thing to the standard production function, and that's this inefficiency term called UI. That's a common way to describe it, and it's something you can't observe, so it's an error. And that makes the model something that has a composite error. Of course, if you have two components to an error, they cannot both be same type. So what happens is one of them has to be different. Well, they have to be different. So the inefficiency term is a one-sided, which means it's non-negative. That's how we separate them. Otherwise, you cannot separate them. Then the VI becomes this is a standard OLS type error, and it's just symmetric. Of course, it's centered around 0. So that's the basic model. This came in 77 and from two different sources. That's quite interesting. Two different books, one European, one American. This is a famous model, but this is a basic one. Of course, you can have different distributions. Simple ones would be normal, as here, and that's what it is. So what makes this stochastic? Why do you say stochastic production frontier? I created this when I am teaching to explain why it's called stochastic. Because if you have a normal production function, you have an equation that you estimate. If it's a Cobb-Douglas with one input, for example, it would be just that one. And then it would be just a line. And you would have errors. But what makes it stochastic? Well, stochastic is because if you add the noise term to this equation, then the actual frontier has that noise term. For an individual, there is a separate frontier for every individual, depending on what the error is. Now, what is that error? Well, let's go back. What is this catching? What's the normal error catching? It's catching all the things that affect production, but you don't observe. So it could be, if I don't have soil quality in my model, well, people with better soil quality would tend to have a positive BI, and you don't observe it, but that's their frontier. The maximum they should be producing should be equivalent to what that soil allows. Okay? So that's why it's called stochastic frontier. So the frontier isn't the same for everyone. The frontier is different, but there is an average. So when you measure efficiency of observed input-output combinations, then you are not measuring the efficiency against the line, but against the stochastic frontier, which includes the noise. I pulled out this table recently. This is by one of the people who created the model, the European ones. They do something interesting. What they do is they take 10 industries, glass production, milk production, and so on, textiles, and then they estimate a standard Koch-Douglas model. And they estimate this composite error. What they are calling composite error, this is 77, is before everyone agreed to call them stochastic frontier models. It's SFA model. And they do something very interesting. Measure elasticity, which is basically coefficient estimates, and then compare them. And this is one of the things everyone needs to remember about stochastic frontiers. If you look at the coefficients will have a lot of similar. Doesn't matter whether you use OLS or SFA, the coefficients will always be similar, except the intercept. This is important to remember. You are not going to improve a lot your understanding of the elastic estimates and so on by using SF. It's more about efficiency measurement. Okay. They showed this back in 77. That's the same year it was created, and every time someone does research, they expect to get a different set of estimates. You don't. It's going to be a similar story. So it's a very useful reminder that OLS still will tell you the bulk of the story other than the inefficiency. So that's the basic model. You can make it more sophisticated by doing different things. Instead of half normal, you could go truncated normal, which came a few years later and was harder to estimate because the software is not good. Then you can go exponential, which is a simpler form. You can go gamma, but gamma is more complex, and even stata. I think some of you have tried stata to estimate gamma. You send it, it never comes back sometimes, depending on your data. So when you go to final data, it becomes more complex. What it allows you to do is, well, it's data collected on a cross-section over time. So you can do more. You don't have a simple cross-section where every observation I is independent or a time series data. You can do efficiency analysis with time series data where you have observations on one entity over time, but you have both. You have data repeated measurements and in individual T time periods. Now you can do more. Okay, even some of the farm data that was collected or got from consultants and was used by researchers here was panel data on the farms. What we do with a panel data model was, one thing is to ignore the panel structure, collapse it into a cross section. That's what they call the pooled data model. But that's not going to allow you to expose the data. If there are heterogeneity or individual effects, then you are ignoring it. Because when you turn it into a cross-section data, you are ignoring the connection between observations on the same individual over time. And if that individual tends to be very inefficient, you are ignoring it, or more efficient, you are ignoring that. For example, you can have cases where, because of heterogeneity, the frontiers are different for different producers, or some of the producers have persistent inefficiency. For example, their labor force is under a union, okay, and that type of stuff. What has been happening until recently? Well, there have been different models. They differ in the sense that some of them might assume individual effects are inefficiency or heterogeneity, or both inefficiency and heterogeneity. And some of them might ignore the fact that there is a transient component. So if they ignore the transient component and just focus on the persistent component, sometimes they take it as constant. So somebody is always 80% efficient. But some of the models have allowed for inefficiency decay. So you would expect, if there is a long time period, you would improve their efficiency somehow. And they call them this time variant versus time varying. There are different models, but all these are not general models. They are ignoring some components. They don't distinguish between heterogeneity and efficiency. All farm effects are inefficiency. So you need to really step up and do something better than ignoring some components, especially assuming that inefficiency is always persistent and there is no transient component, and vice versa. So what has happened recently? What has happened is, because the software is also improving, we have a general model. The general model allows for both time invariant heterogeneity and inefficiency, as well as for transient inefficiency. It's called a generalized true random effects model. The name comes because Green had these models called TRE, true random effects models. It has got two types of inefficiency, persistent, transient. Persistent is, of course, something that depends on type of firm or its management style, whereas transient is a factor that change over time. Could be things that have to do with the company not adapting to things changing, and it looks like this. That's what it is. But we have now 4 errors. What do we do with this? We struggle with one error about heteroscedasticity, autocorrelation, and so on. Now we have 4. And what are they? Well, the first is form effect. This is the heterogeneity. Okay. Second one is our usual OLS type noise component. Third one is the persistent inefficiency, and the fourth one is transient inefficiency. Now, if something is persistent, it doesn't have a T subscript because it's constant for an individual over time. If it's something that's varying for an individual, then it will have a T subscript. So how do you work with this? Well, of course, there has to be some structure to help you work with that. And that structure is, well, the heterogeneity thing has to be two-sided, obviously. Somebody could be better than average or less than average. So it has to be two-sided. The noise term obviously has to be two-sided. The persistent inefficiency, because it's inefficiency, will always be positive. So it's positive, constant over time, but for an individual, but one-sided, and the time varying is one-sided. So this structure is going to help you. Otherwise, you can't distinguish between the errors. Even then, it's not easy. You can have the recent panel data models for Stochastic Frontier analysis as special case. If you remove heterogeneity, then you have a model that has only persistent inefficiency and transient inefficiency. It has no name. It doesn't have a special name. Okay. If you remove persistent efficiency but recognize heterogeneity and transient inefficiency, this is Green's 2 random and fixed effects models. Okay. The random versus fixed is whether you assume this is an error or whether you assume it's a parameter, as in standard stuff. If you remove the heterogeneity and also remove the transient inefficiency, but assume that inefficiency is persistent only, then you have the older type models, which are the fixed effects and random effects models. And if you remove the persistent elements, heterogeneity and persistent efficiency, then you just go back to the 1977 model. So if you have time, you can play around with this to see which ones work and what type of likelihood ratio to investigate and so on. So this has been around since 2014, so it's only 7 years. There has not been a lot of work done on it. How do you estimate this? So if it's 7 years old, okay, it means there might not be much choice in terms of estimation. And it's difficult because it's more complex. More complex, more errors. There have been suggested methods. I think in Kumbakar's book, there is a multi-step procedure. So you have to do panel data estimation, draw the random effects, and then do further estimations to get multi-step ones. But there is simulated maximum likelihood estimation. What I have been doing, I have the APR package from 2013. I keep adding stuff to it. I decided to add the GTRE model to it, and that's what Fu has used for his models. So Bayesian estimation. Of course, Bayesian is not just about estimating it. Then when things go wrong, you can also impose theoretical constraints and so on. And that's what has been happening. Just quickly, this is my APR command for it. So instead of plagiarizing Alexandre's stuff, I decided to just show this. This is what he did. He gave a seminar here when he finished. So I will walk through a few of his slides to just describe what he did and what he got. Tanzania has a lot of regions, including Zanzibar, of course. When we looked at the data, we decided to exclude the island, so just the mainland. What he is, it's an East African country. It has got about 60 million people. That's not a small population. That's bigger than Kenya, is it? I mean, yeah. So Tanzania is not a small country. It's a quite peaceful country, but not small. Crop production accounts for about a third of the agricultural GDP, which means there is a lot more other things happening. It's mainly directed at food production and also cash crops. There are different agroclimatic zones in the region. And in terms of the data, and you can work both on livestock and crops. Of course, if you go into livestock, life is complicated. So it's using the crop data here, wildlife production, and for inputs here. So that's just a summary. We can skip this. And he estimates some variances. We have done this before in terms of discussion.
Professor?
This is just a summary of what he gets in terms of estimates. So these are the GTRE with gamma distribution for the inefficiency terms, the GTRE with truncated normal, the two random effects model, which ignores persistent inefficiency, and the standard random effects, which ignores transient inefficiency and heterogeneity. So we are just trying to see how much things change. So what you see from here is, except for the standard random effects SFA model, which seems to give a different set of estimates, the others are not far from each other in terms of estimates, except for the intercept, of course. Because the intercept will vary a lot because you are allowing for heterogeneity, you are allowing for persistent efficiency, but in terms of elasticity, okay, even with sophisticated models, we get same story as what the people from 7.7 got. The elasticity estimates are not highly sensitive to specification. This is what's called the deviance information criterion. If you have a Bayesian model, this is similar to your AIC. So the smaller the AIC, the better the model. And in this case, of course, the random effects model is the worst one. But the TRE seems to be not much. And there is no clear rule how smaller it has to be before we say this is better. Overall picture, well, there is inefficiency. There is a good amount of inefficiency, but most of it is transient inefficiency. The persistent inefficiency is smaller. So the production shortfalls are usually from people not being able to adjust to changes over time or bit factors that are varying, could be agroclimatic or they respond to things and so on. So overall efficiency is in the 70s, but that's transient and that's persistent. So and in a way, this is also what Phu got for his rice data in Vietnam. The story is dominated by transient inefficiency. So overall efficiency about 73%, and regions differ. Some are stagnant, some of them are catching up. So they are improving efficiency and so on, but this is only short period, 8 years. So I will stop here. So the floor is open for questions, comments. Yes, Ben.
Yeah. So I'm sort of interested in the story about technical efficiency. I seem to recall that one of the challenges is to actually get your production function to represent sort of reasonable economic parameters, and the Bayesian approach is possibly useful in this, but you seem to be shifting it so it's actually a Cobb-Douglas.
The model.
Yeah, is that quite a strong assumption, or is that okay?
Yeah, I forgot to
avoid using a transform at all costs.
Yeah, in fact, this is a very good question. Okay, what Ben asked is very important, and I was at the UWA, the European Workshop on Efficiency and Productivity Analysis, some years ago, and there was a famous person who works on index numbers. So there are two famous people on index numbers. One is the Canadian Dewart, who worked on flexible functional forms and so on, and the other one is Kurt Bolk in the Netherlands. So these guys work on efficiency, and Bolk was presenting on the Cobb-Douglas, and he had done a lot of work trying to show basically how good the Cobb-Douglas could be. So I can't remember, one of the famous economists raised his hand and said, for many, many decades, we have been working hard to get rid of the Cobb-Douglas. What are you doing right now? So I just directed. So it's restrictive. Obviously, it has got limitations, but sometimes, given your data, you have to make a compromise. I think that's what I am seeing. With Phu's data, for example, among the stuff that I have known very well recently, with Phu's data, for every model he used, he did a translate. It works perfectly because that's the Vietnam data. It works. So there is no reason to go to the Cope-Douglas. If you do a test, the Cope-Douglas gets rejected. With the Tanzanian data, for example, we did try. If you go from the Cope-Douglas to the translog, the story gets lost completely. So what happens is you go from this 3 or 4 coefficients to 15. Most of them are not significant. You cannot tell any story, and that's what's happening. So I don't know what it is, whether it's the quality of the data or whether it's the sample size. If the sample size is not big and you have so many parameters and the quality is not also high, what's going to happen? The story is going to get lost in the estimation. So the Cope-Douglas, I don't know what the actual term would be, somebody really observed, but it seems it's having some kind of a comeback. Maybe 20 years ago, people would just throw out your papers and okay. But no, I don't think people are that harsh on the Cope-Douglas. You could write a Cope-Douglas, and if you say, well, the translog was messy, I think they are willing to start.
I think it's more of a data issue because
Yeah.
with all these new variants of things that are coming,
Yeah.
and even with the ones where the code is available,
Yeah.
most of the time we realize they just store data or simulated data to try and illustrate these methods. But when you subject them to really empirical data, then you find that it's very hard to estimate the model. So that's why the Cope-Douglas, I think, is so important. We come back to simple popular.
Because it's simpler, less things could go wrong. Yeah, that's what's happening. And there is value in simplicity. I mean, most of the data we work on is noisy. Yeah.
So I don't fully understand the trend. How you what really is meant in this context by transient inefficiency and so on. But
yeah.
So you've identified that transient inefficiency was the main type of inefficiency.
Yeah.
Is that a common finding, or is that an unusual finding in this study?
Well, we have had food doing the same thing, the ones that I'm familiar with. It seems to be the case, and you would expect. Let's go back to the meaning of transient inefficiency. Means that somebody's shortfall in terms of what they do relative to the maximum they could do stays the same over time. So a company, for example, which has its employees under a labor union, okay.
So it's permanently inefficient.
Permanently inefficient, okay. The transient is more about how its shortfall from the maximum varies over time.
Does it imply that efficiency gets less over time, or just that efficiency
It could be
varies
both.
over time?
It could go up and down.
Okay.
Jumbo, yeah.
Could that be the sample being too short?
Which one?
Who starts at very short period, very short time?
Yeah.
Not sure how long this.
4 time periods: 2008, 9, 10, 11 to 14, 15. If you are working on persistent efficiency and the time period is long, assuming that the efficiency of someone stays the same over time for such a long time, it can be a strong assumption. And that's why the standard random effect models are criticized, because if it's a 20 time period, that's a long period. And that's why they came up with these models that assume that someone's efficiency varies over time along a trajectory, like a polynomial function. So they had those things like Batsy and Corley and others. If you are not identifying transient efficiency, only persistent one, and if it's a long time period, it's difficult to assume that's constant. So what they do is, well, they say there is a trajectory. So they sort of, you could show whether people are catching up or whether they are falling behind. But unfortunately, when it's the same trajectory for everyone, which doesn't make sense. That's what they
The
do.
model assumes it's the same for everyone.
Yeah.
I mean, if you take a farmer,
Yeah.
does a specific farmer, can you test whether they've got a different distribution of the transient efficiencies? So I mean, it's occurring in each year. So you might see for farmer A,
Yeah.
they tend to be the ones that have more transient inefficiency than farmer B, who is transient efficiencies or inefficiencies almost close to zero.
Yeah.
So
So
is there sort of some complex sort of pattern?
in standard SFA, you can have a different efficiency distribution for the farmer using what's called Z variable. So what you do is you go back here. So if I go to the basic model, I can make the mean of the distribution or its variance depend on Z variance. And this is common. This is what's called one stage. So you estimate this story about how efficiency distribution varies between producers as part of the overall estimation. This is one stage. If you don't do that now, if you first estimate efficiency and then go back, do another regression, that's the second time you have a hard time getting people to accept that. You can do that, but subject to software limitations, you could do the same thing with the general model. And in fact, what I showed you here in my APAIR package with Z variables. Too small. Can you see it now?
Yeah.
Okay. You can decide to add heterogeneity, you can decide to add persistent inefficiency transient, and then you can decide to make the mean of the persistent and or the transient or the variance dependent on variables.